not real exact, and it's kind of funny how they measure them. Every belt's measured a little differently. Some are measured from the inside, some are measured from the outside, some are measured from the middle. So if you pick up one belt and you think, and you look at it, you read it, you say, oh yeah, look, that's a 58-inch belt. Gee, I wonder where they measured that 58 inches. Did they measure it on the inside? Did they measure it on the outside? Did they measure it in the middle? And you got to know which kind of belt it is in order to know how they measured it. But the fact of the matter is that this is more important than the past. They've got the manufacturing down so good now that what they call belt matching is almost not needed anymore. But it used to be when you bought a set of belts, they would have a number on them, and that number would tell you if it was a little bit over or a little bit longer or a little bit shorter than the way it was supposed to be manufactured. So if it was supposed to be 60 inches, it might have a number on it to say, well, it's about 59 and 15/16ths. Or it's about 60 and 1/16. And that's fine. You can adjust for that unless you have multiple belts. And if you're putting multiple belts on, you can't put one on that's 59 and 15/16ths and one that's 60 and a 16th, because that ain't gonna work. Something's gonna be flying off of there real fast. So, but that's become, from what I understand from Goodyear and some of the other companies, it's almost a non-factor anymore. The belt matching, they almost don't have to do that anymore. They've got the manufacturing processes down so good now that that's really not a big factor. But we're gonna watch a video here. It's a little bit older video, but it's a pretty good video. It goes through the different kinds of belts. It goes through when you're going to use what belt. And it's a good lead into what we're going to talk about. And then we'll kind of walk through what you're eventually going to do in the lab, which is you're going to determine by looking at different applications, what belt do I need to use. And the other thing we want to look about is how do you tell when a belt is going bad, and how do you tell when a shiv is going bad, which is real important. And it was kind of interesting when we trained the Eco Lab guys, who are doing this every day. None of them ever thought about checking a sheave. So they're out there every day doing maintenance work, and we said, do you ever check the sheaves? How do you check a sheave? Well, I mean, you can do a visual inspection, but there's other ways too. So, it is something that not everybody out there necessarily knows. And again, we're trying to teach you guys some stuff that you go in there and you go up there and say, hey, have you checked, this belt keeps breaking, I wonder why, I don't know, check sheave? Oh, no, check the sheave. It'll make you guys seem like you're really smart. Right, dog? Mm-hmm. Absolutely.
Today's industrial marketplace is transmission products. Power is harnessed with such efficiency that production moves forward at an incredible pace. A pace maintained by the efficiency of power transmission components. This program will focus on a small but crucial component of the power transmission process, the V-belt. The program will explain why V-belts are so effective, detail their advantages, and show how to identify and select the correct style of belt. V-belts are simply transmitters that effectively link a power drive to a needed function. The belts are easy to select, simple to install, and offer years of reliable performance. The first V-belts appeared in the early 1900s. They were cut from leather and fabric, and they replaced existing drives which used rope running in V-grooves. Modern V-belts are constructed differently. They are made of natural and synthetic fibers and rubber, but they still utilize the original wedge concept to harness power. The wedge-shaped belt fits into the wedged groove of the shiv to create a matched fit. When the drive is activated, the pulling power comes from the action of applied tension, which forces the belt to wedge tightly into the shiv groove. By using the wedge principle, the V-belt gains the advantage of tremendous gripping power. Besides this power advantage, the V-belt offers many other advantages for industry in its efforts to reduce equipment repairs and minimize downtime. When an operation demands efficiency and minimal maintenance, the V-belt drive is the logical choice. Unlike roller chain, V-belts require no lubrication. They offer smooth starting and running. They cover wide horsepower ranges. They permit a wide range of driven speeds. They are quiet and efficient. They dampen vibration between driving and driven machines. And they act as a protective device, because they refuse to transmit a severe overload of power, which could damage equipment. Finally, V-belts wear gradually, making corrective maintenance simple and easy. V-belts are so effective that even when proper installation and maintenance procedures are neglected, the belts will operate with some degree of success.
Good example.
That looked like an head assembly.
A V-belt is designed around two concepts, strength and flexibility.
Take me shot.
The strength is provided by a row of tensile cords.
I had 3 shots.
The cords serve as the load-carrying component and are made of twisted synthetic fiber. The compression section is made of synthetic rubber. It supports the tensile cords evenly and compresses while bending around the shifts.
Yeah, it is.
Conversely, the tension section located above the cords is designed to stretch as the belt bends around the shifts. The cover or top fabric is made of a rubberized fabric designed to provide wear resistance and increase belt flexibility. In more recent years, belts with a cog construction have become popular for specific applications. The cogs offer greater flexibility, and with proper usage, it is possible to get up to 25 to 50% more belt life than a standard V-belt. The cogs make it possible to use smaller diameter pulleys, resulting in more compact drives. Additionally,
It was
standard
coming, it was
V-belts
coming.
generally have an ambient temperature limit of 140 degrees Fahrenheit. A cog belt can operate slightly above this limit because of its ability to minimize heat buildup.
That's nice.
While the V-belt's basic design may be simple, the applications demanding its services are complex. That's why the standard V-belt has evolved and expanded to fit the needs of industry. The increasing demand for higher productivity has resulted in a wide variety of V-belt designs capable of handling specific applications. Each V-belt type is a specific design for a specific function, and the identification nomenclature is different for each belt. The differing ID numbers make identification and selection simple. This allows for quick replacement and minimal downtime. If the ID numbers have been worn away, the belt size can be checked by using a V-template gauge. The most common belt type is the classical or conventional V-belt. The classical is also known as a multiple belt because one or more belts of the same cross-section can be used on one multiple drive. Typical applications for the classical V-belt include industrial fans, blowers, conveyor drives, oil field equipment, and agricultural equipment. Classical belts are also available in the cog construction. The dimensions of the classical belt are identified by the prefixes A, B, C, D, and E. Each prefix indicates a standard top width of the belt in inches. For example, A indicates 1/2 inch top width, and B indicates 5/8 inch top width. The classical belt is also available as a cog belt, offering a higher capacity. The cog belt prefixes are AX, BX, and CX. The second size dimension is length. The true length of a classical belt is defined by a datum length. The digits indicating the nominal size represent an approximate inside length. For example, an A42 belt indicates a top width of 1/2 inch and datum length of 43.3 inches. The approximate inside length is 42 inches. Another common belt type is the fractional horsepower or single V-belt. FHP belts are light-duty belts used when the prime mover is a fractional horsepower motor or small engine.
Now, what do they mean by
Typical
fractional
applications
horsepower?
include appliances and many small machines in industry and around the home.
Less than 1. Any motor that's less than 1 horsepower, you need a fractional horsepower belt.
Prefixes 2L, 3L, 4L, and 5L. But while the digits in the classical designation indicate inside length, the digits in the FHP belt indicate approximate outside length. For example, a 3L380 belt means a 3/8 inch top width, the L indicates light duty, and 380 means 38 inches outside length. Another popular belt type is the narrow or V-series belt. Although narrower, their tensile and load-carrying sections are as strong as those in the classical belt. The narrow belt is designed this way to allow for more work in less space. The applications are the same as classical belt applications, and the belts are used with multiple drives also. The narrow belt works best with compact drives, drives of lesser weight, and drives needing greater horsepower capacity. Cog construction is very popular for narrow belt applications, and narrow belts also use the X to denote cog construction. Top width designations for narrow belts are 3V, 5V, 8V, 3VX, and 5VX. Narrow belts are measured by effective length in a standard measure pulley, or the approximate outside length of the belt. Therefore, a 3VX 450 belt would indicate 3/8 inch top width and 45 inches approximate outside length. The X indicates a cog belt. The need to resist drive instabilities brought about the joined belt. Joined or banded belts consist of 2 or more belts whose top fabric is joined to create one unit. This design is effective for pulsating drives that would cause single belts to turn over in the pulleys. Joined belt ID numbers use the same top width designations as the classical and narrow belts. To get the part number, simply add the number of belts as a prefix to the standard belt number. For example, a 3 belt wide BX75 belt would be labeled a 3BX75, the 3 designating 3 belts, and BX75 for the belt size. The great variety of drives and innovative machines has brought about the need for a number of belts for special applications. A good example of a specialty belt is the double V or hexagonal V belt. While the driven shafts on most machines rotate in the same direction, some applications call for the shaft to rotate in a direction opposite to that of the driving shaft. The double V belt was designed for these drives because the belt will drive from either its top half or its bottom half. The construction of a double V belt is similar to the classical design. Therefore, the ID numbers are easily identified as AA, BB, and CC. And AA42, for example, is the same as the A42 or AX42 on a standard measure pulley. Other specialty belts have appeared in recent years, and with the advent of different drives, these belts are in great demand. One specialty belt with a very specific function is the variable speed belt. Variable speed belts are designed to provide speed variation in a drive by working with adjustable shifts. Other specialty belts include open-end V-belts, V-ribbed belts, and dry can belts. Even though the ID numbering system for V-belts is standardized,
End of video presentation. So that's a really good video on belts, and I'll have David put that up on the blackboard for you. That'll be a good review probably to look over before you have to take your next assessment. So, you know, when you get really good at this, and maybe some of you are, especially some of you guys that are car guys, you know, I know David, he can look at one of these things hanging on the thing and say, oh, that's a B42X, you know, he can just rattle it right off. I can't do that. So I'm going to pass these around, and you can see that on this this larger belt, it's you know, if you look on here, this is an A58. So what kind of belt would that be? It's an A58. What's that tell you about it? It's a classical belt because it's A, B, or C, right? And it's a 58, so that's going to tell you something about its length. Now, I don't know if you remember, but again, in the classical belts, that's the inside. On the fractional belts, it's the outside. And then on some of the specialty belts, it's actually the center. So that's kind of interesting to know too. And then I'm going to pass these around. I wish I had one of these for each of you, but I don't. But we'll put one on each table. But if you go on Goodyear's website, you can download the PDF of this. And this is installation, maintenance, and the troubleshooting guide for all the belts that Goodyear makes. So this is something that would be handy to have. When we showed these to Ecolab, they were just really excited to get it. Man, we never got one of these before. So this is, you know, if you got to download the PDF, or you might even be able to write to Goodyear. And actually, I'm going to call Allied, who gave us these, and see if we can get a couple more to take a look at them. Yes, Ed?
On this, it says 1812 MX89, and then I need to go to that. What are those?
I have no idea, but that's what counts right there, the A58. That's the important thing. So if you look in this guide that I passed out, you'll notice it has a lot of information about different belts. This is another, we won't put these charts up, this is another chart that has the same thing. So I mean, they're talking about these specialty belts. There's all kinds of specialty belts. If you look in your printer at home, you'll probably see a belt that's driving the print head that's a very thin cogged belt. And that's a specialty belt. It's a timing belt. So this has that type of thing. The variable speed belts, it talks about that. There's high torque belts, which are belts that are especially for high torque. There's torque flex, which are belts that are high torque and can be very flexible. They have specialty belts that, depending if you know that you're not going to have good alignment, belts that can withstand that type of thing a little better than others. But part of what you're going to be doing in this particular lap is figuring out, how do I size a belt? So we're going to talk a little bit about that. So we've already talked about the three types of belts. In the video they call it the classical belt, but I think in your book, they call it classical or conventional. So you got classical or conventional, and you got the fractional horsepower. It took me a while to figure that out. That didn't hit me right away. Well, what's the difference between a fractional horsepower and a conventional? And essentially, there is none. It's just the fractional horsepowers are made to be used in a smaller power and horsepower situation. And then the last one that was not in the video, but is in the book, in your book, is called a wedge. And the wedge is the one that's actually measured in the middle instead of the inside or outside. So you'll see when you look in the lap, they talk about that wedge. And then of course they all can be cogged. Every one of them can be cogged. Now, one of the belts I handed around, you'll notice, didn't have any numbers on it, did it? It's the one that Jeffrey has back. Isn't that someone? Which one doesn't have any numbers on it?
That's the clip.
There's one that I passed.
It's got B37.
That's gonna be, okay, maybe I didn't pass that one around. Maybe it's still over here on the cart.
Yeah.
Ah, here we go. No, that's not it. That's where we had one that had numbers on it. Ah, here it is, here it is. When it's cog belts. No, that's good. That's it. I swear we had one that had no numbers on it. We do not. Anyway, if you do have one that doesn't have any numbers on it, that's when you use this. So this is called a belt gauge, and this one is for wedge belts, and it tells you right on this is for wedge belts, and this one is for torque flex belts, IT torque flex belts, and I'm assuming the one for wedge belts would also work for the conventional belts and so what you're going to do is you're just going to put it in there, and it's going to tell you whether it's a 4V, a 3, 5V, or an 8V. You put it in here, it's going to tell you whether it's an A, B, C, or D. So you're going to take the belt, and hopefully it will work. And you're going to stick the belt right down in here like that. So what size is that?
That's a B.
Okay, so that's a B belt. Is it a B belt? Let's see.
Yeah.
So gun, B37.
So,
How about that?
would you use those to check for wear?
Yes, you would do that too. So you put that in there and you see is that if I'm seeing space in there, this thing is starting to wear, right? If it may start to cup is what they typically will start to do, is they'll start to get a little bit of a cup in it. Or maybe one side's fitting in, the other side isn't fitting in. So that must mean for some reason it's wearing on one side and not on the other side, right? So that's how you use this. So if you have a belt you can't identify, you use these, and you're going to do some checking with these when you do this particular lap. And then see what else we have here. So the biggest thing, or I guess you're going to do some identification on some belts and determine the size of them using the gauge, determine the size of them using a ruler. You're going to talk a little bit about the quick disconnect bushings and how to size them, so that's going to be part of the lap as well. And then how the sheaves are specified. Now in a sheave specification, it's going to look something like this. You're going to have a number, and then you're going to have a letter, and then you might have another number, and this might actually have a decimal in it, and then you're going to have another letter designation. So that's how a sheet is going to be identified. So if you look at any sheet that's over here, and I don't know if these are identified that way, we'd have to look on it real carefully. Yeah, this one is AK32X58, and that doesn't seem to fit the designation that we've got shown up there, so that might be a different one. Let me see if one of these does. Group sheet, weight sheet, that's not it. Web sheets, nothing either of those do. I'll find one that does with questionnaire. These double ones do. Yeah, 1BM50. So it's usually going to be stamped right in there, on the inside of there, what the sheet is going to be. So the first is the number of grooves. So that's a one groove sheet, right? So if it has multiple grooves, like this one does, then this is going to start out with a 2. It's a 2 groove sheet. You could have 3 grooves, you could have 4 grooves. So this first one is the number of grooves. Then the next designation, the letter designation, is going to be what type of belt that it's for, right? So because this says B, what kind of belt does that tell you it's for? Is it for a, yes, for a classical, right? Because it's got a B. Then the next one's going to tell you what the diameter is, right, in inches. So this is a 3.4 diameter belt sheet. And then the last one, the SH, is going to tell you the size of the bushing. So this needs an SH bushing. So that's the designation of the sheet. And again, it's in your lap, so you'll want to look at that. Sheets have 2 identifying diameters. They have the actual outside diameter, and then they have what's called the pitch diameter. The pitch diameter is where the center of the belt is going to ride. That's called the pitch diameter. The outside diameter is literally the outside diameter of the sheet. So you want to know that type too.
Now, is that 3.4, is that the outside diameter?
I think the 3.4, I have a feeling, is the pitch diameter. Let me see if it says that in here. Sheet diameter can either mean the pitch or the outside, depending on whether it's fractional horsepower or conventional wedge. With fractional horsepower and wedge, the sheet diameter is the outside diameter. With classical, it's the pitch diameter. Since that's a classical belt, then that would be pitch diameter. So that's good to know. So this is the pitch diameter on classical, and it's the OD on fractional horsepower and wedge. So that's good. A good question there, Dave. And then, just like with the belts, you want to check the sheaths with the sheath gauge. And it's going to be basically the same thing. You're going to take and you're going to find the right sheath gauge. You're going to actually put it down in the sheath itself, and it should fit right in there. Right? And if it doesn't, then the sheath is starting to wear. And this was something that the techs at Ecolab had never seen. They've never seen a sheath gauge. Where'd you get those? I said, oh, here, we hand them all. A set of them.
That's hard to imagine that a sheath would wear out with
Well,
belt?
it probably will in in a harsh environment where maybe you have dust, you have grit, you have something like that that's, if you get that and then you got that in between the belt and the pulley, then you got sandpaper.
Yeah.
And that's going across it all the time. So I think it takes a while, but they will wear out. And I know that one of the guys from Ecolab had said they had never seen one of these, but they had a belt they were constantly replacing this belt. All of a sudden, they were constantly replacing this belt, and they couldn't figure out why. It was fine for years, and now we're replacing it every 3 months. What's the difference? And then somebody said, well, I wonder if something's wrong with one of the sheets. And sure enough, they checked it, and one of the sheets was really severely worn.
What was worn on the sheet?
It'll cup. It can cup out like this so that you're not getting good contact, and that can also cause slippage too. Because it's all about the reason these work is as they get under torque and it pulls that belt in, it makes a really nice tight tractional fit. But if you've got some cupping going on the inside of the sheath, on the inside of the belt, then all of a sudden it's like having if your tire was cupping on the road, all of a sudden you don't get very much traction. Right? It's just the same principle.
Also, rust causes that.
Yeah, rust can cause it. A lot of these belt drives are in some pretty harsh environments. I mean, you saw the ones like on the outside, on this outside equipment, on carnival rides and stuff like that, where it's raining and it's snowing, and you got temperature change, and they're in some pretty harsh environments. You think about even the belt, your serpentine belt on the motor in your car. You got a lot of heat involved. You got oils and stuff like that involved. Grit, road grit, salt in the wintertime. All kinds of harsh things that can wear on the belt. So that's what these are. In part of the activity, you're going to be using one of these to check a sheath. But of course, all our sheaths are in pretty good condition because they're brand new. So they should. If you find one that's worn out, let us know. We'll be surprised. So the next thing that you're going to need to do in this particular one is selecting a belt, and that is a 10-step process. So I'm going to go through all the steps on the board, so you'll see that process, and then you're going to go through it as well in the lab. So there's 10 different steps. Now, if you look at different stuff on this, different material. I was looking at the Bates website, Gates. And they make, of course, a lot of different belts. And theirs was a 9-step process. So it's kind of like who do you go see, and they're going to give you the process. But the first thing that you want to do is determine the design power for the power requirements. So usually that's going to be as simple as figuring out what horsepower is the motor. However, that's not the only thing. You've got to also figure into that what they call the service factor, right? Because if I choose a belt for a 5 horsepower motor, and I don't think about what environment that motor's working in, I'm probably undersizing that belt. Right? If it was in ideal conditions, which means it has a service factor of 1, then I'm fine. But service factor of 1 would be this: intermittent service, 3 to 5 hours daily. Okay, and it'd be for things that have very little harsh environment type of things like blowers, exhaust fans, centrifugal pumps, fans up to 10 horsepower, and light duty conveyors. So if you had any of those things and they were only operating 3 to 5 hours a day, and you had a 5 horsepower motor, you could size your belt for a 5 horsepower motor. That's a 1, right? And this chart is in your book, and I also think it's in that book that we passed around, if I remember right. And then as you go up, there's like 2 parts to this chart. One is down this way, and as you go down this way, the numbers go up. So even if I was in an intermittent 3 to 5 hours of service, that's pretty intermittent service. When I get down into things like crushers, hoist, rubber extruders, mills, again, you're thinking, I got dust, I got all that stuff, then my factor goes up to 1.3. Right? So as I get into more harsh environments, it goes up. And then going across this way, it's the duty cycle. How much am I using it? So for example, even if you were just using something on a fan, it's just blowing a fan, pretty simple operation. Well, if you're doing that continuously between 16 to 24 hours a day, and it's an AC motor with a high torque, and a high slip propulsion, then that's going to be a 1.3. So you have this service factor, this multiplier that you've got to multiply by. The very worst would be a 1.8. So you think about that, that means if you have a 5 horsepower motor, you have a service factor of 1.8, you almost have to size your belt for almost a 10 horsepower motor. Very close. Right? So that's how this is going to change. So what you'll do is you'll figure out what is the environment that I'm using the belt in, and then what's my service factor. So when you determine the design factor, you figure out the horsepower plus what's called the service factor. And not plus, times the service factor. So if I had a 5 horsepower motor and I was in a 1.3, I would be sizing essentially for a 6.5 horsepower motor. That's essentially what, so when I pull the belt, I'm going to look on the chart, I'm going to look at 6.5. Even though I'm only using a 5 horsepower motor, I would want to size it for 6.5. So that's the first thing you do. And then the second thing you do is determine the belt selection. So you go right to the belt selection chart. And this is only, when you do this, in the book there's 2 ways, it shows 2 ways to do it in your lab. And the first way to do it is you're going to take and you're simply going to look at the design horsepower, and it goes down this side, and you're going to pick the belt, and there's going to be more than one. There's going to be probably a conventional belt, and then if it's under 1, of course, there'll be a fractional horsepower belt, and there might be a wedge belt selection. There might be a cog belt, a non-cog belt, so you have those options. So you're going to read across and you're going to pick the belt selection that you need. And then the next thing you need to determine is the drive ratio. So the belt selection, this would just be from a chart. And you're going to use this number right here. And you're going to select the one over that, because that might not be on the chart. If I look on this chart, there's no 6.5. It goes from 5 to 7.5. I'm going to go 7.5. I don't want to go under. I want to go over. So in this situation, if I had this 6.5, I could use a BX, I could use an AX, I could use a B, or I could use a 3BX. That would be my 4 possible choices that I would have. Now, so the third thing that you're going to determine is your drive ratio.